Hello everyone. Today we are going to discuss basic type of functions. This topic helpful in limits, continuity, differentiability, and in case of differentiation and applications of derivatives. Also useful in integral calculus as well as calculating area. Basic functions are very helpful. First, we are going to discuss polynomial function and then we go for rational function. After that, we will discuss algebraic function and then we go for exponential, logarithm, modulus function, greatest integer function and signature function as well as fractional part function. These basics are very important. Let us discuss first about polynomial function. Polynomial function, nothing but the function should be of the form f of x equal to a0 plus a1x plus a2x square and so on an x power n. In 8th standard, you studied the topic polynomials, right? The function, suppose it is of the form f of x equal to a0 plus a1x plus a2x square and so on an x power n for all small x belongs to capital R and here small n belongs to whole number and here the coefficients a0, a1, a2 and so on an, they are real values. If the function is of this form, then it is known as polynomial function. Let us discuss different examples. See the definition with clarity. Here a0, a1, a2, an, they are coefficients of x, x square and so on x power n. They must be real values and exponent of x, that is small n, that should be whole number, nothing but non-negative integer quantity. Suppose for example, if I write a function f of x as 2x plus 3, clearly it is a polynomial. Why? Because here coefficient of x2 and constant 3, they are real values and here the exponent of x, that is belongs to whole number, non-negative integer, so that it is a polynomial. Another example I am going to write. So f of x equal to 2.3 into x square minus 4.5 into x plus 11. This one also a polynomial. Why? Because here the coefficients 2.3 minus 4.5 and here the constant 11, they are all real values and exponent of x, it is 2, it is 1, they are clearly whole numbers, so that by the definition it satisfies the conditions, implies it is a polynomial. One more example I am going to write. Suppose f of x equal to x to the power of 1 by 2 minus 75. This is not a polynomial. Why? Because here exponent of x is a fraction. It does not belongs to whole number, remember, so that it is not a polynomial. One more I am going to select. Suppose f of x equal to 1 whole divided by x plus 3. It is also not a polynomial. Why? Because 1 by x plus 3, that is reciprocal of polynomial x plus 3. It is not a polynomial, it is reciprocal of polynomial x plus 3. The function should be of the form a0 plus a1x plus a2x square and so on an x power n. But here in the reciprocal, the form you have like a0 plus a1x and so on an x power n, so that it is not a polynomial, remember. So these are the examples how to verify polynomial. And let us discuss degree of the polynomial. Here, if an, the constant, if it is not equal to 0, the highest exponent of x is clearly n, that is known as degree of the function. For example, f of x equal to 3x power 7 minus 5x power 4 plus 6 is a polynomial. Here 7 is the highest exponent of x, so that degree of this polynomial is 7. Another example, suppose f of x equal to 5x minus 4. Here the highest degree, the highest exponent of this function is 1, so that it is known as first degree polynomial. First degree polynomial is also called as linear polynomial. And in case if it is of degree 2, suppose for example 5x square minus 3x plus 1, it is known as quadratic polynomial. Due to second degree, it is called as quadratic polynomial. Next, suppose the polynomial function is of degree 3, x cube plus x square plus x plus 1. It is known as cubic polynomial. In case the function is of degree 4, suppose 4 times of x power 4 minus 3 times of x square minus 5. It is known as biquadratic polynomial. So depending upon the degree, if it is of first degree linear polynomial, second degree quadratic, third degree cubic, fourth degree biquadratic, and then fifth, sixth, seventh, they are called simply fifth degree, sixth degree polynomial, like that. If the exponent, highest exponent is n and its coefficient non-zero, then the degree of the polynomial is denoted by n, remember. Next, let us see the graph of linear polynomial first. Suppose f of x equal to, in general I am writing f of x linear polynomial. Suppose f of x equal to ax plus b. Linear polynomial like y equal to mx plus c. You know that y equal to mx plus c indicates a straight line. So f of x equal to ax plus b indicates a straight line. This is the graph of linear polynomial, remember. Next, second degree polynomial. Suppose f of x equal to ax square plus bx plus c. The graph of second degree polynomial that represent a parabola, and that is of U shape, remember. Next, if it is of third degree, suppose f of x equal to ax cube plus bx square plus cx plus d. Here a not equal to 0, and here second degree a non-zero, here third degree, so that a not equal to 0. Third degree polynomial that represents a curve, it is of the form, it is of this shape, third degree. So depending upon the degree, we get the graph of polynomial. Clearly, all the polynomials are continuous on its boundary. Polynomial functions defined for all x belongs to R. Already in the definition you have x belongs to R. That is, input any real number, and on its domain observe linear, quadratic as well as cubic graphs. They are continuous. Here also it is of continuous graphs we get. So that I can say that polynomial functions are continuous on R. Now I am going to write properties. First, property number 1. Polynomial functions, they are continuous on their respective domain capital R. Okay. Next, second property, range of the polynomial function. Range of f of x, that is, I can say subset of R. Let us see. You know that linear polynomial, that is a straight line. Range of straight line. Range value is nothing but set of values of y. Range from minus infinite to plus infinite. It continues. So that here its range is, I can say R. It is clearly subset of R. Next, second degree polynomial, if you choose, that is a parabolic shape graph. So the range of this parabola starts from here up to infinite in the upward direction. It starts here and goes up to infinity. So that clearly this portion is subset of R. In the same way, whatever the degree of the polynomial, its range must be subset of real values. Next, I am going to write another property. Property number 3. If suppose f of x plus f of 1 by x, if it is equal to f of x multiplied by f of 1 by x for all x belongs to R minus 0, x value except 0. Why? Because you have 1 by x here. If suppose a function satisfies this functional rule, f of x plus f of 1 by x equal to f of x into f of 1 by x, then the function f of x is polynomial of degree n, and particularly that is f of x equal to plus or minus x power n plus 1. Remember, only this function satisfies this functional rule. Nth degree polynomial with the coefficient highest term coefficient is plus or minus 1, and then you have a second part that is only constant term. Next, property number 4. Polynomial functions continuous over. Now we are going to discuss about differentiability. Polynomial functions are differentiable on R. You know that suppose if the graph is having sharp edges or some gaps, or sometimes the graph jumps like this. Wherever the function has sharp edge and wherever the function has little bit gap and wherever the function jumps, at that place the function is non-differentiable. Remember, here the functional value of this function f of x does not exist. So there is no discussion about continuity at this position A. Next, second one, the function has sudden jump. Suppose it is defined at A here, then also it is non-differentiable. Why? Because differentiation nothing but that indicates slope of the function at that point, right? Here there exist so many tangents at that point to the given curve. You know that differentiation is unique for every function, but here for this function there exist so many tangents, nothing but so many derivatives we are going to get. That is not correct. Only the unique differentiation, unique derivative exists for any function, nothing but unique slope exists. But here there are so many slopes exist, so many tangents exist. In the same way, so many slopes we are going to get at this corner, so that it is non-differentiable. Next, suppose the function has sharp curve, sharp edge. At this sharp position there exist so many tangents to this function. When it has so many tangents, nothing but so many slopes exist. So many slopes, nothing but derivative is not unique. In this case, when derivative is unique, then only the function is differentiable. Why? Because for each and every function, differentiability at a point is unique result, but here we are going to get so many, so that sharp curves, gap curves and jumped curves are non-differentiable. And just now we discussed polynomial functions, linear, second degree and cubic polynomials. They are straight lines and U-shaped parabola and curve like N-shaped third degree. These are doesn't have any sharp edge or gaps or jumps, so that I can say that polynomial functions are differentiable on real values, real number set. Okay, next we go for another function. Second function, that is rational function. We are familiar with rational numbers. The numbers are of the form p by q, q not equal to 0, p comma q are integers. But here it is not rational number, it is rational function. Rational function nothing but the function of the form f of x by g of x. Denominator part g of x is non-zero quantity, and here both numerator as well as denominator, f of x and g of x, they must be polynomials. Remember, no other functions, only the numerator and denominator consist both polynomials. Then the function of the form f of x by g of x non-zero quantity is a rational function. For example, suppose that there is a function f of x that is equal to 2x minus 3 divided by x square minus 4x plus 3. Here the condition x square minus 4x plus 3, it is not equal to 0. It is a rational function. Why? Because both numerator and denominator are polynomials in x. Numerator is of degree 1, denominator is of degree 2. Linear and quadratic polynomials in the numerator denominator, so that it is a rational function. Another example I am going to give, f of x equal to x square minus x plus 1 whole divided by x square plus x plus 1. X square plus x plus 1 denominator part not equal to 0. That is x any real value. Why? Because it is irreducible second degree. It is also a rational function. Why? Because both numerator and denominator, they are polynomials, remember. Suppose if you have the function f of x equal to 3 power x divided by x square plus 1, it is not a rational function, remember. Why? Because numerator that consists exponential function 3 power x, nothing but that is exponential function. In the definition given that both f of x and g of x must be polynomials. Here it is of exponential and it is of second degree polynomial. If both numerator and denominator polynomials, then only it is rational, otherwise it is not rational, remember. This is about rational function. Let us move to the next one. Next function, algebraic function. You are familiar with algebraic operations. You know that algebraic operations nothing but like addition, subtraction, multiplication, division, extraction of square root, etc. These are algebraic operations. And here the function is algebraic function. Nothing but here a new function which is obtained by applying algebraic operations on polynomial functions. That is known as algebraic function, remember. What I am saying, a new function which is obtained by applying algebraic operations like addition, subtraction, multiplication, division, or applying square root, cube root, etc. Particularly here you have to use polynomial functions, remember. What I am saying, a function obtained by applying algebraic operations to the polynomial functions is an algebraic function. Here you have to use polynomial functions for which you have to apply different types of algebraic operations like addition, subtraction, multiplication, division, or extraction of square root, cube root, whatever it is. See, for example, I am going to write a function f of x, that is square root of x square minus 5 plus 3x minus 2 divided by 7x square minus 5 plus 3x. It is clearly algebraic function. Here the algebraic operations are square root, plus sign, minus sign, division, and then here subtraction, addition. So that here there is a new function f of x. It is formed by applying different algebraic operations to the polynomials x square minus 5, 3x minus 2 and 7x square plus 3x minus 5. Such type of functions are called algebraic functions, remember. One more example I am going to write. Suppose f of x equal to 3x square minus 5 into x plus 2 whole divided by square root of x square plus x plus 1. Here the algebraic operations, multiplication in the numerator, and here you have division, next extraction of square root. So that here there are three polynomials, second degree 3x square minus 5, and a linear expression here x plus 2, one more second degree x square plus x plus 1. These three are polynomials and they are with algebraic operations, multiplication, division and extraction of square root. So formed a new function f of x. Such type of functions are algebraic functions, remember. Next, let us move to the another function. Next we will discuss about exponential function. Exponential function. Exponential nothing but exponent means rapid. Maybe the graph rapidly increases or rapidly decreases. A function, if it is of the form a power x, here a is base, x is exponent, and it is defined for all x belongs to R, and the condition to the base a more than 0 and a not equal to 1. This is known as exponential function. F of x equal to a power x for all x belongs to R, but the conditions a more than 0, a not 1. Why not a 1? Why not a negative? Question mark. Let us discuss whenever base quantity 1 and base quantity minus 1, and then we go for what happens when base value between 0 to 1 and more than 1. What I am saying, actually by the definition given that a value positive but not 1. Suppose that this is a, the values of a more than 0 and given but not 1. Suppose a in between 0 to 1, what happens? And whenever base value more than 1, what is happening? First observe, and then we go for what happens when base value 1 and base value negative. See, in case base value in between them, if I select 1 by 2, and here more than 1, suppose if I choose base value 2, see the graph of f of x. Now f of x become 1 by 2 whole power x, and here f of x equal to 2 to the power of x. Let us observe these two graphs. Give input x value 0 first. What happens? 1 by 2 power 0, nothing but 1. When you give input 0, functional value become 1. Next, if I give input 1, 1 by 2 whole power 1, that is 1 by 2. Next, if I give minus 1, 1 by 2 power minus 1, nothing but it goes to 2. Substituting the values of x in the same way, we get the graph like this. This is rapidly decreasing. You know that exponent nothing but rapid. Yes, it is rapid graph. Next, and clearly rapidly decreases when base value between 0 to 1. Next, suppose base value more than 1. For example, if it is 2, what happens? When you write 0, 2 power 0 become 1. If you write 1, 2 power 1 value 2. Next, if you write minus 1, 2 power minus 1 nothing but 1 by 2. Joining all these points, we get a graph in increasing manner. Yes, clearly it is having rapid growth, rapid nothing but exponent. So, whenever base quantity between 0 to 1 and more than 1, we are going to get a rapidly increasing or rapidly decreasing graphs, so that these type of functions are known exponential functions. What happens when base value 1 Let us observe. In case if I select base value as 1, if base value 1, the graph exists consistently. Suppose 1 power x. If you write x value 0, 1 power 0 nothing but 1. If you write 1, 1 power 1 again 1. Next if you write 2, 1 power 2 again 1. If you write minus 1, it is 1. If you write minus 2, again 1 power minus 2, nothing but again 1. So for all real values of x, the graph is constant, the graph maintaining constant. There is no rapid growth and there is no rapidly decreasing in the graph, so that this graph is clearly constant graph, so that it is not rapid whenever a value equal to 1. That's why 1 is removed from the base. Next, why not it is negative? Let us discuss. In case if you select base as minus 1, clearly when the value of x is 1, y value become minus 1, right? Minus 1 power 1, nothing but minus 1. Next, if the exponent x is 2, that is even number, minus 1 whole square, that become plus 1. Next, if you write x value 3, minus 1 whole cube, minus 1. So sometimes it is minus 1, sometimes it is plus 1, sometimes it is minus 1, so that it is oscillating plus 1 minus 1 like that. So this is not rapid function. Due to that reason, base should be either more than 0 more than 0 particularly, but not 1. Remember, this is about exponential function, and you can say that the graph clearly it is continuous on its domain, and it is also differentiable on R. Why? Because there is no sharp edge and there is no gap and there is no jump in these two graphs, so that exponential function continuous as well as differentiable on R, remember. And domain of this function is set of all real values, but its range, the range of the graph is clearly positive. The graph is forming entirely above x-axis, so that range of the function 0 to open 0 to infinity, only the set of positive values. I am going to write the properties. Exponential function. Exponential function, it is clearly continuous on R, and it is differentiable on R. Next, its domain, set of all real values. Next property, its range, open 0 to infinity. There are two graphs for exponential function depending upon the base. Maybe the graph decreases or maybe the graph increases depending upon the base. And here the first graph, it is decreasing graph, so that base value between 0 to 1, remember. And second one, that is the graph when base value more than 1. Next, fifth property, the function f of x equal to a power x satisfies functional equation f of x plus y equal to f of x into f of y. For all x comma y, they are real. This functional equation satisfied by the function f of x equal to a power x, remember. You know that the property of exponents a power m plus n, nothing but a power m into a power n. So with the help of that, I can say that f of x plus y equal to f of x into f of y, like a power m plus n equal to a power m into a power n. So if the function satisfying this condition means the function that must be exponential. And property number 6, f of x equal to e power x for all x belongs to R. It is also an exponential function, and here e is irrational. It is known as Euler number. Euler's number it is, and the value approximately, e value approximately 2.718. remember, this is base e. E is nothing but a number, and that is approximately 2.718, and it is irrational, remember. This is about exponential function. And then we go for logarithmic function. Next function, logarithmic function is defined by f of x equal to log x to the base a for all x more than 0, base value a for which the condition a more than 0 and a not equal to 1, remember. This is the definition of logarithmic function, and logarithmic function it is inverse of exponential, remember. For example, 2 power 3, you know that this is 8. Left hand side it looks like a power x, and its result is output y. It looks like y equal to a power x. Here input x equal to 3 and output y equal to 8, and base value here 2. What I am saying, logarithmic function it is inverse of exponential, I am saying. Suppose there is a function f mapping from a to b, then its inverse defined from b to a, remember. So input changes to output, output changes to input. Usually logarithmic function written as y equal to log x base a. In the exponential function you have input 3 that as output in the logarithmic. Next, output in the exponential function that you have to write as input for its inverse logarithmic with base 2. Clearly, just logarithmic function which is inverse of exponential, remember. And exponential function has 2 different types of graphs, that is depending upon the value of base. Base value between 0 to 1 the graph decreases, and base value more than 1 the graph increases, right? Now let us observe the graph of logarithmic function. Y equal to log x to the base a, and here the condition 0 less than a less than 1. Next graph, y equal to log x to the base a, condition base more than 1. We know that it is inverse of exponential. First I am going to draw the graph of exponential, and then we go for logarithmic. Whenever the base value between 0 to 1, exponential graph, that is clearly decreasing graph, right? Yes, you have to draw the graph in a decreasing way. This is the graph of y equal to a power x depending upon base condition. Next, when base value more than 1, exponential gives increasing graph. This is the graph of a power x. Just now we discussed logarithmic, which is inverse of exponential. Suppose f contains set of order pairs x comma y, then its inverse f inverse contain order pairs y comma x. So the values of x comma y interchanges. I can say that the graphs are symmetry about y equal to x. You will get symmetric graph about the line y equal to x, remember. So that now you have to draw symmetric graph with respect to the line y equal to x. This is y equal to x. This is y equal to x. Now you have to draw symmetric graph. Symmetric to all these points, we get a graph here, and for next these set of points goes to like this. So this is the graph of y equal to log x base a when base value between 0 to 1, remember. Again it also decreasing. In a decreasing manner we get logarithmic graph. Clearly this dotted lines as well as thick line, these two graphs are symmetric about the line y equal to x. X changes to y changes to x in case of f and f inverse. Due to that reason we get symmetric graph about the line y equal to x. Next, here also the same symmetric graph about the line y equal to x you have to draw. Clearly its image about y equal to x here, it goes like this. This is the graph, this one. This is y equal to log x base a and condition a more than 1. Exponential increasing way, logarithmic also in increasing way when base value more than 1, remember. This is about logarithmic function. Next, let us discuss some properties. Property number 1. Log x to the base, it is defined for all x more than 0. It is defined only for positive values of x. Next point, range of the function. Range of log x base a is set of all real values, remember. Why? Because there are two graphs. When base value between 0 to 1, decreasing graph, base value more than 1, increasing graph. Both the graphs defined from minus infinite to infinite. Minus infinite to infinite exist, so that range is set of all real values. Next, property number 3. Clearly the two graphs are continuous and differentiable on its domain. I can write continuous and differentiable on r plus in its domain. Domain only the set of positive real values. Only this side we are going to get the graph. So I am going to write r plus. Next, property number 4. Suppose the functional equation f of x into y equal to f of x plus f of y. Product transfer into sum. It is possible only in logarithmic function if and only if the function should be logarithmic, remember, log x to the base, and here the conditions x comma y belongs to r plus only. Why? Because the function defined only for positive real values of x. This is property number 4. And you have different properties of logarithm we will discuss now. You know that log a power m, that can be written as m of log a. Next, log a power m base b power n, that can be written as m by n log a base b, and log 1 to the base, it is always 0, remember, and log a base a, the value is 1, and log ab written as log a plus log b, and log a by b is log a minus log b, and also log a to the base b written as reciprocal of log b base a. Input and base you have to write reverse, and also it is written as log a divided by log b. This is the last property, and these are very important properties in logarithm. And graphically we observe, when you put x value 1, the functional value becomes 0. So here the graph is y equal to log x, output y 0 when you give input 1, so that log 1 to the base, the result become 0, and log a to the base a, that become 1, remember, and product changes to sum, division changes to difference, and log a power m is m into log a, and also you have log a to the base b, that is 1 by log b base a, or you can write log a by log b. Next, we go for modulus function. Modulus function is also called as absolute value function or positive function. It is denoted by f of x equal to mod x, and it is x for positive values of x, 0 when x equal to 0, it is of minus x whenever x values are negative. See the graph. Particularly at 0, functional value is 0. So 0 comma 0. Next, for all positive values of x, f of x is nothing but y, and y clearly equal to x. X, y both are same when x is positive. See, here it is 1. It is 1. 1 comma 1 here. 1 by 2 comma 1 by 2 here. Next, 2 comma 2. X and y both are same. 1 by 2 comma 1 by 2, 1 comma 1, 2 comma 2, 3 comma 3, 4 comma 4. So joining all these, we get a straight line. Clearly that is y equal to x. Set of points on this line whose coordinates x, y both are same, so that we get a straight line there. Next, for negative values of x, it is minus x. So if you put minus 1, that gives positive 1. If you write minus 2 as input, then you will get plus 2. So joining all these points, we get another line, that is y equal to minus x, remember. So that mod x graph that has sharp edge at x equal to 0, and clearly that is of V shape, remember. The graph is in V shape and it has sharp edge here. So I can write the properties now. First property, here it is of V shape graph. Next, property number 2, it has sharp edge at x equal to 0. That means not differentiable at x equal to 0. That is differentiable on r minus 0. Except 0, there is no sharp edges. So that it is differentiable on r minus 0, but not differentiable at x equal to 0. Next, third property, there is no gap. The graph is continuous. Sometimes it is decreasing and sometimes it is increasing without gap, so that it is continuous on R. And we know that mod x plus y always less than or equal to mod x plus mod y, mod x minus y greater than or equal to modulus of mod x minus mod y. Inequality holds in case of plus and minus, and for multiplication and for division equality holds, remember. You can write equal to mod x into mod y here, mod x divided by modulus y here. And you can easily remember first two results. You know that in any triangle, sum of two sides always greater than the third side. Sum of two sides independently, mod x plus mod y, that is always greater than third side. In such a manner, you can easily remember this. And difference of two sides, this one, that is always less than the third side. So in this way, you can remember these two results. And equality holds in case of product and division, remember. These are the properties in modulus function. And also observe here the line y equal to x, which makes an angle 45 degrees with positive direction of x-axis in the counterclockwise sense, and another line y equal to minus x that makes an angle 135 degrees with positive direction of x-axis in the counterclockwise sense, remember. This is about modulus function. Next, we go for signature function. Or signum function. Signature function is defined by signature of x, that is equal to minus 1 for negative input, 0 for input 0, plus 1 when the input is positive. This is the definition of signature function. Here input nothing but domain of this function, set of all real values, but range, here observe the output, that is only set of 3 values that containing minus 1, 0, plus 1. These 3 outputs you have, so that range is a set that containing just 3 elements, minus 1, 0 and plus 1, and domain is negative, positive as well as 0. so that set of all positive real values exist for signature function. And the graph of the function, signature graph on Cartesian coordinate system, when x value 0, it is 0, this is over. Next, for negative values of x, it is -1, signature value, functional value, that is y equal to -1, nothing but line parallel to x axis. This is y equal to -1. Next, for positive values of x, it is 1. Positive values of x, it is 1. Y equal to 1, line parallel to x axis. This is the graph of signature function. It has 3 outputs. Remember, 0, +1, -1. Next, suppose if you have signature of signature x, what happens? Suppose signature of signature x, then what is the result? Observe. Internally, signature of x 0, +1 and -1. So here we are going to give input 0, positive and negative quantities. When you give 0, signature 0, 0, signature 1, positive values, so that 1, signature -1, negative input, so that it is -1. Again we get same outputs, so that simply it can be written as signature of signature x, that is again signature x. Remember, SGN indicates signature of x, again signature of x. So any number of times you can apply signature for signature functions. Finally that gives the result signature itself, nothing but output again -1, 0, +1. Remember, this is about signature function. Usually computer commands, they are depending upon zeros and ones. Remember, so here signature function indicating here the importance for zeros and ones in the case of signature function is, I think it is developed, signature function is developed with outputs 0 and 1 depending upon computer code language. That is, you know, that is always the commandings in terms of zeros and ones. Maybe that is helpful there. Next we go for greatest integer function. Greatest integer function, this is also called as step function, or we call floor function also. Suppose f of x equal to, greatest integer function is defined by f of x equal to closed bracket x, and it gives output x whenever the input is integer quantity. Remember, in case if input is non-integer quantity, then you will get greatest integer left side of x. What I am saying, whenever the given input is integer quantity, step x value again integer. If it is non-integer quantity, then you have to write greatest integer left side of x. For example, you have the question, what is the value of step 2.1? On real line, somewhere it is 0, 1, 2, and assume that here it is 2.1. Step 2.1, nothing but clearly given input is non-integer quantity. For non-integer quantity, you have the result greatest integer left side of x. It is possible to decide greatest integer only in the left side. There are so many greatest integers in the right side, so that it is impossible to decide greatest integer in the right part of 2.1, but in the left hand side 2 is the greatest integer, so that greatest integer of 2.1 is 2. Next, suppose the question greatest integer of 2.9, here it is of 3, here it is 2.9, greatest integer again left hand side you have to observe, that is greatest integer 2. Let us discuss different examples. Suppose the question step 7.1, step 7.3, step 7.9 and step of 7.9 bar. What is step 7.1? You know that left side only you can decide the greatest integer, so that greatest integer of 7.1, 7. What about greatest integer of 7.3? That is again 7. Why? Because left side the greatest integer of 7.3 again 7. Next 7.9. For 7.9 we get 7. And here the question is 7.9 bar. 7.9 bar, it is same as 7.9999 and so on. What is greatest integer of 7.9 bar? Usually students says the answer 7, but it is 8, remember. Why? Because it is clearly 7.9 bar is nothing but 7.999 and so on, that is clearly 8, and by the definition step x equal to x when x is integer. Here these are all 7.1, 7.3, 7.9, 7.1, 7.3, 7.9, they are non-integers. 7.9 bar, it is integer quantity and particularly equal to 8. By the definition, whenever x is integer quantity, the same result you have to write. So the same result 7.9 bar is the result. 7.9 bar actually 8. Let us discuss how 7.9 bar equal to 8. Let us suppose x equal to 7.9 bar. 7.9 bar rewritten as 7.99999 and so on. I am going to multiply with 10 on both the sides. What I am saying? Multiply both sides with 10. What happens? 10x equal to, if it is multiplied by 10, what we get? 79.9999 and so on. Now on subtraction, from 10x you have to remove x. It gives left side 9x. And here in the right part 79.9 bar, from which you have to remove 7.9 bar. 79 minus 7, that is 72, and remaining all zeros after decimal point, right? So 9x equal to 72, x equal to 72 by 9, x equal to 8. Actually x is 7.9 bar, 7.9 var x, 8 also x, so that 8 is equal to 7.9 var, and hence step of 7.9 var nothing but step of 8. Due to integer quantities, the result is 8 itself. Next, let us see the graph of step function. X-axis, y-axis, and it is origin. Here 1, 2, 3, minus 1, minus 2, minus 3. You know that if x belongs to integer, implies step x is clearly x. So 0 implies 0, 1 implies 1, 2 implies 2, 3 implies 3, minus 1 implies minus 1, minus 2 implies minus 2, minus 3 implies minus 3. Okay. Suppose 2.1. If you give 2.1 input, then it become 2. 2.2, 2. Step of 2.3, 2.4, 2.5, 2.6, 2.7, 2.8, and so on. We get a step. Next, for 1.1, 1.2, 1.3, and so on, 1.9, it is of 1. Next, you will get the same graph, and here, and here. So this is the graph, and clearly the graphs like steps, so that it is called as step function. And set of values of x in the interval 1 to 2. If suppose input in between 1 to 2, then the value approaches to 1, so the downfall into their previous integer. Suppose x values in between 2 to 3, suppose 2.1, 2.2, 2.3 up to 2.9, if we give input, then what is the output? That is, after applying step value, that decreases. That is, you have to write greatest integer left side of x, so that 2.1, 2.2, and so on up to 2.9 if you write, then the output is 2, decreasing. So in between two successive integers, the values downfall into their previous integer. So downfall means, so they are under the floor, so that it is also called as floor function. Okay, this is about the graph of step function, and clearly observe its domain. It is defined for all x belongs to R. When 2 it is 2, when 1 it is 1, and in between 1 to 2, 2 to 3 also it exists. Second property, range of the function. Range is set of all integers, only 0, and then jumps into 1, and then jumps into 2, 3, minus 1, minus 2. So set of all output values of this function is known as range, and clearly range set of all integer quantities. Next, third one, it is continuous on r minus z. Remember, it breaks, it discontinuous particularly at integers, and then continuous, and there is a break, and then continuous. After each integer it is going to take a break and then continuous, so that it is continuous on r minus z. And also you can say that differentiable on r minus z itself. Wherever the gap is there it is non-differentiability. Why? Because many number of tangents exist at that integer quantity, so that it is non-differentiable. Next, fifth property, step of x plus integer, that can be written as step x plus integer. I is nothing but integer quantity. See the property. Suppose x plus integer, step of x plus 2. you can write step x plus 2. It is possible only when the constant is integer, remember. Here, if I select the value of x, suppose 1.2, what happens? Observe, are they equal or not? When x is 1.2, 1.2 plus 2, nothing but 2.2, and it gives the result 2. This is LHS part. Next, in the right part, first step of 1.2, that is 1, and then plus 2. So 1 plus 2, step 1.2 value 1. Here it is 1.2 plus 2, that is 3.2, and hence it is 3, remember. So LHS is 3, RHS also 3. So this is possible only in case of integers. This is very important property. And another property, step of x plus step of minus x, that is 0 when x is integer, minus 1 when x is non-integer quantity. Let us see this property carefully. Step of x plus integer is step x plus integer, where I is only integer. This is over. Next, what I am saying, step x plus step of minus x, it gives two outputs, either 0 or minus 1, depending upon the values of x. If x is integer, your answer 0. If x is non-integer, then your answer minus 1. Let us verify with an example. Let x value suppose 2.3. 2.3, that is non-integer case. Next, suppose x equal to 3, that is integer case. Now let us observe step 2.3 plus step minus 2.3. What happens? Step 2.3 is 2 and step minus 2.3 is left side integer, that is minus 3. And finally on simplification we get minus 1. Left side of minus 2.3, the greatest integer is minus 3, so that you will get minus 1. And here in case of integer, step 3 plus step of minus 3. Step 3 value 3. For integer it is integer only. So plus of minus 3, it is 0. So whenever integer, it is of 0. When it is non-integer quantity, the result is minus 1. This property is very important. These are the two properties. Next we go for fractional part function. Fractional part function is defined by f of x equal to fractional part of x, that is equal to x minus step x, and that is defined for all x belongs to real. This is the basic definition of fractional part function. Very simple. Suppose if you have fractional part of 2.7, that is the question. Clearly observe, in 2.7, 2 indicates integral part or integer part, and 0.7, that is the fractional part. So in which the fractional part is 0.7. And in case if you have just 3, clearly 3 integral part, it means there is no fraction so that 0. If suppose input is minus 2.7, in case of minus 2.7, usually students says the answer 0.3, but that is not correct. Sorry, usually the student says answer 0.7, that is not correct. 0.3 is right answer. Why? Because the logic applicable for 2.7 and 3, the same logic applies for negative number also. You know that here fractional part of x, nothing but x minus step x. So the same logic, x minus step x, you have to write. Here x nothing but 2.7 minus step 2.7. That is 2.7 minus step 2.7 value 2. Therefore, difference gives 0.7. The same logic, x minus step x, you have to apply here. Minus 2.7 minus step of minus 2.7. This is minus 2.7, and then step of minus 2.7, that is minus 3. Outside you have minus sign, become plus 3. So the difference 3 minus 2.7, that gives the result 0.3. Remember, this is about fractional part. And see the graph. Different examples I am going to give. After that we go for graph of fractional part function. Suppose if you have 7.1, what is your answer? Fractional part in this 0.1. Suppose if you have 7.234, then what is your answer? 0.234. Suppose 77 is there is no fraction, so that your answer 0. Remember, only for negative values, that is different. Don't write 0.1 or minus 0.1. It is of 0.9. Suppose fractional part of minus 7.7 if you have, what is your answer? 0.3. Next, minus 77. It is clearly integer, there is no fractional part, so that we get 0 answer. Okay, for each and every fractional part number, the logic, fractional part of a number is the logic applied here, x minus step x. Remember, so for negative numbers, here minus 7.1, suppose if you have, you feel that minus 8 is integral part, 0.9 is fractional part. Fractional part non-negative, remember, and the values of fractional part, if you observe, it starts with 0 and up to 0.9 and so on, but not exactly 1. Remember, let us see the graph of fractional part function we are going to discuss now. F of x equal to fractional part of x, and it is x minus step x, and defined for all x belongs to R. See the graph. Zero, 1, 2, 3, 4, minus 1, minus 2, minus 3, here minus 4. Assume that here it is 1. Particularly, if you write integer quantities, fractional part 1, 1, fractional part 2, 2, fractional part 3, 3, fractional part minus 1, sorry, fractional part 1, 0, fractional part 2, 0, fractional part 3, 0. There is no fractional part, 0, fractional part of minus 2, again 0. So for all integer quantities, it is 0, remember. Next, if you write 1.1, what happens? 0.1 is fractional part, so just 0.1. 1.2 means 0.2, 1.3, 0.3, up to 1.9. This is the graph. Next, 2.1 means 0.1, 2.2 means 0.2 fractional part, 2.3, 2.4, 2.5, for which fractional part 0.3, 0.4, 0.5 and so on. So the graph exists in this way. So this is the graph of fractional part, and the graph repeats at 1, so that we can say that it is periodic function. The graph is periodic and its period is 1, where the graph repeats like origin. The graph at origin, the same graph repeats at 1, 2, 3, 4, but the least positive real number is known as period of the function. So period of fractional part of x, remember, it is of 1 unit. And different properties we are going to discuss here. Let us see the graph. Here the domain of the function set of all real values, right? Already in the definition it is defined for all x belongs to R, so that domain R. And range of the function, range is nothing but set of all output values. Observe this graph, outputs only in the interval 0 to 1 the graph you have, it includes 0 but doesn't includes 1, so that range you have to write closed 0, open 1. Clearly the graph discontinuous at integers, therefore I can say that it is continuous on R minus Z. Also it is differentiable on R minus Z. Yes, clearly at integers it discontinuous, so that there exist so many tangents at that integral part, so that at integers it is non-differentiable. So R minus Z is differentiable part. Next, fractional part of x plus integer, that is equal to fractional part of x, where I is integer. Fractional part of x plus integer, since I is already integer quantity, there is no fractional part, so that you have to write fractional part in this, so it is equal to fractional part of x, remember. And fractional part of x plus fractional part of minus x, that is 0 when x belongs to integer, and when x is non-integer quantity it is 1. Let us see an example. Suppose x value 1, what happens? Fractional part 1 plus fractional part minus 1, no fractional part, no fractional part, their sum 0. This is the first result. Next, for non-integers, suppose x equal to 1.1, what happens? Fractional part 1.1 plus fractional part minus 1.1, that is 0.1 plus here negative 1.1, for which fractional part is 0.9, so that 0.1 plus 0.9 gives the result 1, positive 1 whenever x is non-integer quantity and x is integer, the result is 0. These are the properties of fractional part function. So these are the basic functions which are helpful in different concepts, different chapters like limits, continuity, differentiability and applications of differentiation, and also helpful in definite integrals, areas, and in case of differential equations. So the students, those who are aspirants of IIT JEE, they must concentrate on basic functions with here you have to remember all the conditions, particularly in the basics what we have the conditions, those conditions you must prepare well, then only you can give correct answer. Otherwise it is impossible to solve different types of problems which are given in the examinations. The students, those who are thorough in basics of functions, they can easily solve lengthy questions by graphical methods within 2 or 2.5 minutes. So that be concentrate on basic functions topic. Thank you so much.